Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to calculate the density of a wire given the crystal structure nature of the substance itself. So let's get into this. So in this problem we're told that the substance known as memory wire is an alloy of nickel and titanium. It's a crystal structure. Its crystal structure is body-centered cubic BCC. The corner atoms are nickel and the center atom is titanium. The average atomic radii of nickel and titanium are 124 picometers and 147 picometers, respectively. Calculate the density of this alloy. Okay, so let's get into this. So the first thing we want to do is remind ourselves what the density is and what the ratio is, or what it means. So density is a relationship between the mass and the volume. It's the amount of mass per volume. So if we write that down, density is equal to the mass over the volume. So all we need to do is find the mass of this substance, find the volume, and then divide. So easier said than done. Let's go ahead and try this. So we're talking about the density of a substance, and we are given the fact that this is a body-centered cubic structure. The atoms are how should I say, they're organized in such a way that gives them a particular structure. And then this structure is called a body-centered cubic. And what does that mean? So here I have a picture of the cubic structure, and I didn't put the atoms in because I think it would get complicated. But basically what it's saying is that at each corner are nickel atoms. So at each of the 8 corners here, I have a nickel atom. So if I was to draw one corner, right, so it would look something like this, right? So I'd have a nickel atom in that corner. And you can see that this is only the cubic structure of one cubic cell of the entire structure. So this cell is next to other cells. So this face of the cell is shared with another uh, cell here. So this face here is shared by a cell that would be up here. This face would be shared by another cell that was next to it. This bottom face would be another cell shared. So I'm only drawing one cell. So if you can imagine, this nickel atom here is actually being shared by 8 or 7 other cells. This is the corner. This corner is shared by 8 total cells here. So that means that the mass of this atom is divided evenly into 8 parts. So 1/8 of this entire atom is found within this particular cubic cell here. The other 7/8 are in the other 7 cubics. Now I know this is probably hard to imagine, but just trust me here. So here, maybe this part of the atom is actually found inside that cubic volume. But keep in mind that each of these corners also has a nickel atom, 1/8 of which is found inside that this volume here. So when we're trying to calculate the mass of the substance, we're only interested in the mass of the atoms that are within this particular volume here. Because all of the cubic cells that we're going to be looking at are identical, so if we can figure out the density, the mass divided by the volume, if we can figure out the volume of this cube here, and all the mass of the atoms in this volume, then we can calculate the density, and that's going to be the same throughout. So all we need to do is figure out how many atoms total of nickel plus the titanium is in this cubic volume here. So we already have part of the answer. We said that the nickel is nickel atom is at each of the 8 corners, and each atom of nickel, 1/8 of that atom is found within this volume here. So we have 1/8 of an atom, excuse me, we have 1/8 of a nickel atom in the volume from this corner, but we have 7 other corners. We have 1, 2, 3, 4, 5, 6, 7, plus this one. So we have 8 corners. We have 1 nickel atom at each of the corners. 1/8 of each of those atoms is actually inside this space here. So 1/8 of each of those 8 gives us a total of 1 nickel atom. So let me write that out. So we have 1/8 of a nickel atom at each of the corners. We have 8 corners, so if you multiply that by 8, 1/8 times 8 gives us 1 full nickel atom inside our cubic space. Okay? Now, what about the titanium? Titanium, we're told, is at the center. So at the center, we have 1 titanium atom, and that's it. So at the center, we have a titanium atom. At each of the corners, we have nickel atoms, and that's it. So that means that contained within this space, this 1 cubic space, we have 1 titanium atom plus 1 nickel atom. So that's it. So all we need to now know, all we have to figure out is the mass per atom of nickel and the mass per atom of titanium, and we'll get the total mass that's inside this space, this cell, this volume cubic cell. Okay, so let's go ahead and do that. So since we have 1 atom of nickel, we can convert that into grams per atom. So using the molar mass, we can convert that from grams per mole to grams per atom. So how do we do that? So we look up the molar mass of nickel. When we look up the molar mass, let's see, 5869. So we have 58.69 grams per 1 mole of nickel. We can use Avogadro's number to help us convert moles into atoms. So 1 mole of nickel is equal to 6.022 times 10 to the 23rd atoms of nickel. So we'll use that as a conversion factor. So grams I want to stay the same. So here I have grams on the bottom, moles on the bottom here. So I'm going to have 1 mole of nickel on top and 6.022 times 10 to the 23rd nickel atoms on the bottom. So moles of nickel cancel out, leaves me with atoms. And all I have to do now is take the grams divided by the number of atoms, and I'll get the grams per atom. And when I do that, I get 9.746. 9.746, sorry. 9.746 times 10 to the 23rd. Let me look at that again. 746 times 10 to the, oops, not 23rd, but negative 23rd grams per atom of nickel. And then I can do the same thing with titanium. So I look up the molar mass of titanium, that's 4788. So I take 47.88 grams, and this is nickel, of titanium per 1 mole of titanium. And then I use that, again, Avogadro's number, I'm going to convert moles to atoms. So again, 1 mole of titanium on the top, 6.022 times 10 to the 23rd titanium atoms. Again, moles of titanium cancel out, leaves me with atoms. And then when I divide the grams by the atoms, I get 7.951. 7.951 times 10 to the negative 23rd grams per atom of titanium. Okay, so grams per atom of titanium, let me just double check. 7.951, 7.951. Okay, so now I have the grams per atom of both nickel and titanium. I know I have 1 atom of each. I have 1 complete atom of nickel inside my space here. And I have 1 atom of titanium in the center. So I have 1 atom of each. So that means that I have 9.746 times 10 to the 23rd grams of nickel atom. And I have 1 of these as well. So all I need to do, oops. Sorry about that. All I need to do is add these together. Since this is the number of grams per atom of nickel and I have 1 atom, so that means I have this many grams. And I have this many grams per atom of titanium and I have 1 atom, so that means I have this many grams. So I just add these together. And when I add those together, I get 1.770. 1.770 times 10 to the negative 22nd grams. Okay, I have the total number of grams, or the mass, from both the nickel and the titanium atoms in my space here. So I got the total mass. Now all I need to do is calculate the total volume of my cube. That is a little bit trickier, so stay tuned. Okay, now for the volume. So notice here that I have these different colored lines. And so one of the things that we need to know about the BCC, or the body-centered cubic, is that the atoms that are touching each other only along the center from one corner to the opposite corner there. So you have the titanium in the middle, you have an atom, and then you have an atom of nickel at each of the corners. So you have one at this corner, and you have one at this corner here, and then you've got the titanium in the center, and that is where they are touching. So you can see this orange line goes from this top corner in the front all the way down to this bottom corner in the back. So the radius, if I draw this in a little bit, so you have the radius of, say, this atom here of nickel, and then that's touching the center atom of titanium, and then you've got this corner here with its nickel touching there. And so this is the line through the center of the cube from here to here where the atoms are touching. Okay, why is this important? And I apologize for my really bad drawing here, but I hope you get the point. So what this means is that the center of your nickel atom is here, and then the end here. So that's the radius. So this is going to be the radius of nickel here. And that's the same thing with this here, is you got the nickel atom, and so the center of the nickel atom is at this corner, and it's going to go out to the edge here. That's one radius. So you've got the radius of your nickel atom here. You've got the radius of your nickel atom here, and then you've got the whole diameter of the titanium atom here. So if you add all of those radii together from the two nickel atoms and the titanium atom, you get this straight line here. So we can figure out what the length of this orange line here is by adding up the radii of the different atoms that are touching each other like this. So let's go ahead and write that out. So this is the length C. So I have C here. So this orange line, that's C, that's going through the cube. That's C. And then we have this line here, this blue line is B, and this line here is L. This L is the length of the side of the cube. So you can see I have L here, L here, L here. So this is a cube. So all the sides of the cube are equal to L. So this side of the cube squared plus this side of the cube B, right? Or not the cube, but this line here of this triangle, this is a right triangle. So we're going to use the Pythagorean theorem. So this side of the triangle squared plus this side of the triangle squared is equal to this side of the triangle squared. So that means that C squared is equal to B squared plus L squared. But C, we said, is this line here, which the radii of the nickel atoms and the titanium atom are broken up, are making up. So this line is broken up into those radii. So C, the length of C is going to be equal to 2 times the radius of the nickel. So remember, this is nickel, and this is nickel, and this is titanium. So we have a radius of nickel here, we have a radius of nickel here. So that's 2 times the radius of nickel, plus we got the diameter here, which is twice the radius of titanium. So we have twice the radius of titanium. So that equals C, but C squared. So if we get C squared, that means we're going to have to square this whole thing. And when you square that, I'll spare you the details, but you should be able to square this. So if you square that, you get 4, let's see. So we'll get 4 times R of the radius of the nickel squared plus, where'd it go? It'll be 8 times these two. So we multiply these together and multiply by 2. So we take the square of this to get this one. Multiply these two together and then multiply by 2. We get 8 times the radius of nickel times the radius of titanium. And then we take the square of that. So it gets 4 radius titanium squared. So this is equal to c squared. Now for b squared, b is this here. But notice that this is the hypotenuse of this right triangle. So we have this right here, this side of the cube, which is L. And then we have this side of the cube, which is L. Those are the legs of the right triangle. And that is the B here would be the hypotenuse of this triangle here. So we can use that for B. So B squared is going to be equal to L squared plus L squared. So L squared plus L squared. So we have this and we have this. So we have c squared and b squared. We have c squared and b squared and L squared. So we can take this, substitute it in for c, and then we can take this and substitute it for b. So let's go ahead and do that. So c squared, instead of c squared, we're going to have this. So we have 4r radius of the nickel squared plus 8 radius of the nickel times radius of the titanium plus 4 times the radius of the titanium squared. That is all equal to b squared plus L squared. So b squared is going to be this. So we have L squared plus L squared for the b squared, and then we have L squared. So L squared plus L squared plus L squared is just 3L squared. So basically what we end up with is going to be, let me erase this. I'll rewrite it up here. We're going to have 4r radius of the nickel squared plus 8 times the radius of the nickel times radius of the titanium plus 4 times radius of the titanium squared, and that's equal to 3L squared. Okay, so now I'm going to erase this to give me more space. Now we just need to figure out the radii of the nickel and the titanium. We want this in centimeters cubed because going back to our density, the density of a solid is normally measured in grams per centimeter cubed, where the volume is in centimeters cubed. So we're going to have to convert the radii to centimeters. So we're given these respective radii of nickel and titanium. So nickel has a radius of 124 picometers. We're going to have to convert that to centimeters. So let's go ahead and do that. So we have 124 picometers over 1. So we're going to have to convert picometers to meters first. So 1 picometer is 10 to the negative 12 meters. So we're going to have to use that as a conversion factor. So let's go ahead and do that. So we have So we have on the bottom, we're going to have 1 picometer. On the top, we're going to have 10 to the negative 12 meters. Picometers cancel out. Let me just double check. Yep. And then now we're going to convert meters to centimeters. So I have meters on the top. I want meters on the bottom. Centi means 10 to the negative 2, or 1/100th of a meter. So 1 centimeter is 10 to the negative 2 meters. So I'm going to put 10 to the negative 2 meters on the bottom and 1 centimeter on top. You could do 1 meter is equal to 100 centimeters. That's the same ratio. It doesn't matter. So meters cancels out. When I do the calculation, I get 1.24. So 1.24 times 10 to the negative 8 centimeters. And then I'm going to do the same thing with 147 picometers. So again, 147 picometers over 1. And by the way, this is nickel. We're talking about nickel here. So this is the radius of nickel. So the radius of nickel is equal to that. Here we have the radius of titanium is equal to that. We're going to convert to picometers first. So again, 1 picometer is equal to 10 to the negative 12 meters. Picometers cancel out. And then we're going to convert meters to centimeters. So 10 to the negative 2 meters on the bottom, 1 centimeter on top. Meters cancels out. And again, we get 1.47 times 10 to the negative 8 centimeters. Let me just double check. Yep. Okay, so now we have our radius in centimeters. We have the radius of nickel, radius of titanium. So we can plug this in and now solve for L. So that's going to be a few steps. So let's go ahead and do that. So again, this is the radius of nickel, and this is titanium. So I'm going to go ahead and put this in. Give me some room here. So 4 times the radius of nickel, which is that. So 1.24 times 10 to the negative 8 centimeters squared, plus 8 times the radius of nickel, again, 1.24 times 10 to the negative 8 centimeters, multiplied by the radius of titanium, which is 1.47 times 10 to the negative 8 centimeters, and then plus 4 times, and then the radius of titanium. Let me get rid of this, get this out of the way, which is 1.47 times 10 to the negative 8 centimeters squared. And again, all of this is equal to 3L squared. Okay, so now that I have this, all I need to do is simplify and solve for L squared. So when I calculate this, basically what I'm going to do is I'm going to take the square of this multiplied by 4, and then add that to 8 times this, right? And then add this times 4 times this squared. So you can do that on your calculator. When I do that, I get 2.9376. So I get 2.3976 times 10 2.9376. Oops, what is it? 9376. 9376 times 10 to the negative 15 centimeters squared. And then that's equal to 3L squared. Then what I'm going to do is I'm going to divide both sides by 3. So I divide both sides by 3. So then that cancels out. And then I have this equal to L squared. I want L, so I'm going to take the square root of both sides. So I take the square roots here, and I take the square root there. So then L squared, taking the square root of something undoes the square, so that becomes L. So this is going to be equal to L. And then I divide this by 3 and then take the square root. And when I do that, I get 3.1292. 3.1292. So I get 3.1292 times 10. 3.1292 times 10 to the negative 8 centimeters. Oops, that should be 8. So that is L. So that is the length of one side of the cube. So each side of the cube has the same length. We want the volume of the cube, so it's going to be the side L cubed. L times L times L. So all we have to do is cube the length of the cube, which is L here. So all we need to do now is take this and cube it, and we'll take this and, of course, cube that. So this length cubed is going to be 3.06. 3.06 times 10 to the negative 23 centimeters cubed. L3, which is equal to the volume of the cube, which is what we want. So we have the mass that we calculated earlier. Now we have the volume. So this is going to be equal to 3.06 times 10 to the negative 23 centimeters cubed. So now all we need to do to find the density is to divide mass by volume. So let's go ahead and do that. So then the density is equal to the mass, which is 1.770 times 10 to the negative 22 grams, divided by volume, which is 3.06 times 10 to the 20 or negative 23. Negative 23 grams, I'm sorry, centimeters cubed. So we have a smaller number divided into a larger number. So this means the density is going to be larger than 1. So if we calculate this out, we get 5.78 grams per centimeter cubed. And that, ladies and gentlemen, is the density of this memory wire. So I hope this was helpful. If you found this helpful, if you enjoyed this video and learned anything from this video, then please, by all means, like the video, share the video, hit that like button down here somewhere. Also, do me a favor, subscribe to my channel. Do that now. Click on the notification bell. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or a topic you need me to cover or would like me to cover, put that down below and I would be happy to do that for you. Thanks for joining me and have a great day.